we now come to the point where we formally define potential energy. And potential energy is defined, potential energy U is defined as the work, okay, the integral of the work with a negative sign from some initial point to some final point. So remember that F dot dr is the work performed on an object, and if I take the overall work done in lifting an object from some initial point to some final point, and I attach my negative sign, then this is the definition of potential energy. And we will use this situation to show that the potential energy from the gravitational force is mgh, as we stated earlier. Okay, so now we're going to prove that result. So if I start with an object at point A on the ground and I lift it up to point B, okay, then I'm lifting it up a distance, and that distance is b minus a. So in our formula, h is going to equal b minus a. Now the force that we're working against is gravity, so this is going to be negative mg, and dr is upward, and so mg and dr are anti-parallel, and I can simplify this equation in that situation. This becomes minus negative mg dy, since we're now moving in the vertical direction from A to B, right? And my force mg, especially over small distances compared to the radius of the Earth, is constant, and so I can move it out of the integral, and I'm going to get negative mg integral from A to B of dy. And the integral of dy is just y, evaluated at my endpoints just becomes b minus a. So this becomes mg b minus a, but we said that b minus a is nothing but h, the height that we've lifted it, so this becomes mgh. So the potential energy gained by an object being raised a distance h above the Earth's surface is defined as mgh, and that is again in a coordinate system where up is positive and downward is negative. Now what we will find is actually it does not matter where you define your origin for potential energy's sake. Only changes in potential energy are important, okay? But that is how you can use the definition of potential energy to derive the mgh result, okay? The elastic spring potential energy is given elsewhere, so I will leave it to you to either figure that out on your own using the definition of Hooke's law or look that up. But again, the end result is 1/2 kx squared, where x is, if I have an initial spring of length, some equilibrium length, and then I stretch it a little bit further, then x is that extra distance that I've stretched it. So 1/2 kx squared is the potential energy of a spring, and you can use this formula to derive that result. All right, next video we're going to look at conservation of energy.